Well, thank you. Thank you very, very much for inviting me here. So I was hoping to have something newer to say, but that turned out to be too speculative still. So somebody once commented here about work in no progress. So instead, I will give a kind of a survey of a very long-term project of kind of making sort of Motivic, I'll put it in quotes, representation theory of p-adic groups. So I feel like I've been talking about something like this for, I don't know, 15 years. So maybe I finally understand a little bit about this project. So the project was started by my advisor, Tom Hales, around 99, I think, when I was just starting grad school. And actually, I realized I should use this opportunity to advertise an event. So we're organizing a conference for his 60th birthday, which is hard to imagine. So something unrelated, but maybe this is kind of the most important part of my talk. So in Pittsburgh, June 18th to 22nd of this year. So there is a small poster on, where the poster session is. One of the posters is small and dark blue, and that's the poster announcing this conference. There is a website. I don't want to spend time putting it on the board, but if you Google it for Tom Hales, Pittsburgh, June 2018, you'll find it. So registration is open. It will be open for a long time. We're likely to have funding for students to come, so please come to that event. It will be a conference on many things, not all at once. That Tom does, which is related to what I'm talking about, and formal verification of proofs, and discrete geometry, and automorphic forms. We have a pretty impressive list of speakers, some of whom are present. So anyway, that's my ad. So anyway, so sometime back in '99, he kind of started thinking about using the very new at that time theory of Motivic integration to try to do something for p-adic groups. And that's been going on for a long time now. And so I would like to report maybe on the state of affairs in that project and what it can and cannot do. And everything I will be talking about today is a work of many people. So, well, Hales was already mentioned, so definitely I should mention Francois was there. Well, Jan de Neve should have been mentioned earlier because he's one of the authors of Motivic integration that went into it and started it all. But in terms of active collaborators to this project, it's Raf Cluckers and Halupczok. And Hales has collaborated with Jorge Silly, his recent student, and Bill Kesselman. And I'm pretty sure that I'm missing some people. Hopefully it comes as I talk. But anyway, so I'm largely reporting on a lot of people's work. And so, well, we have to start somewhere. So we start with G, a connected reductive group. Algebraic group. So now, well, the main example for today's talk it could be something like SL2. That's just fine. But generally, you can think about G as an algebraic subgroup of GLN, given by some equations, if you wish. What's important for this project is that we need to kind of be able to build isomorphism classes of algebraic groups as field independently as possible. So what we really should do is start with so we want field independent description. Or rather, we kind of want to see to which extent so I'll put it in quotes because, of course, we can't really have it. But we want to see to which extent we can define the algebraic group that's a priori just a group defined over a p-adic field in a way that's p-independent. So you have to be careful from it from the very beginning. As we're building up later, we want to say something about its representations. Well, we actually won't, but But for now, we start with the classification of reductive groups. And so, well, as we know, so over the algebraic closure, the group is classified by the root system sitting inside. I would just write down a lattice just to emphasize that for now we just start with an abstract combinatorial thing. So for the case of SL2, the picture is going to look like, no, not like this. Sorry, this is I'm drawing an SL3 picture, and I said my example would be SL2, but anyway, SL2 doesn't give you much of a picture. So for SL3, you have an integer lattice spanned by these guys in barycenters of the triangles in the root system. So anyway, it's completely a combinatorial picture. So rather than thinking about this as subgroups of anything, we just start with this completely field-independent picture. So these things classify reductive groups, and well, over the algebraically closed field. So later, because QP is not algebraically closed, we will also have. So what we already see is that we will have parameters. So, for example, to distinguish between forms of a given group over the p-adic field. So, in our case, so for SL, for outer forms, you will have unitary groups versus SL versus division algebras. So, so the parameters, so what we will be doing is we're trying to build everything in terms of formulas in a language that Raf was also talking about. So I just want to kind of start with that. And so the fixed choices are going to be these combinatorial things that are completely field independent, and then you can introduce parameters for the splitting field of your group, write down formulas for the cocycles defining the Galois action, and so on, and so it becomes tedious, and they will of course suppress all these details. But so that's all I want to say about the classification of reductive groups, is that you can define them. So with some ... you will get all isomorphism classes, so all reductive groups over QP up to isomorphism as members of a family of definable sets. So they will be basically, you can think of them as appropriate, no, different button? Yeah, I do mean definable family. I'm also, oh, okay, I see. It's because I'm pressing the stop button. Sorry. Hope I'll figure this out. Okay, stop for now. Members of definable family of definable sets. And so this way, actually, we hit each reductive group many times, infinitely many times, perhaps, as so we don't, well, as you all know better than I do, getting equivalence relations is kind of hard to, well, equivalence relations are hard to deal with. So when we're using, say, Galois cohomology to classify forms of a reductive group, we're just satisfied with having the cocycles. Those can be written in a definable way. We don't care if the two cocycles give you equivalent forms, isomorphic forms in the end. We just, we'll see each reductive group infinitely many times, every time its isomorphism class arises. So rather than trying to make the cohomology groups and classify things. And so, okay, so this is how this thing gets off the ground. If you want to be technical about it, if you don't, then it's completely safe to say just think about classical groups, which are defined by, say, split classical groups, then it's fine. It's just defined by completely nice algebraic equations defined over Z, essentially, right? You can think of an orthogonal group or a symplectic group or something like that, or just GLN. Well, so, okay, maybe what I should say is, so, well, the objects we want to think about are something like G of, well, I will write QP everywhere or G of FPT, but really, or maybe G of K, where K is any non-Archimedean local field. So ultimately, of course, we would be working with the set of points of these groups, right? And so maybe what I should say is that what we can do is, for starters, so we make a family of definable sets. And definable in this DNF pass language, which is three-sorted language for valued field, residue field, and the value group sort. Value group will always be, the normal valuation will always be normalized so that the value group is Z. The symbols here are language of ranks on the valued field and the residue field, and Pressburger language on Z, with extra symbols for angular component from the valued field to the residue field, and the valuation from the valued field to the residue field. Okay, and so the point is that what we can do is we can recover these sets as a family of definable sets in this language, but we should remember that it's a family fibered over some parameters which encode the data. So the family parameterized by the data of the splitting field and the cocycle that determines the Galois action. Oh, okay. Sorry, I'll figure this out shortly.
Eventually changes your different families.
Yes, so for each, I would say this, for each root datum, you will have your own family. So for each of the fixed choices, so for each root datum, you will have one split group, and that's your family member, and then all forms of it come as members of a family of definable sets. And so, unfortunately, so I'd prefer, normally I try not to talk about this little complication, but for some of the transfer results, it will become important later. So just as a preview, the reason I'm paying attention to this right now is that, well, a lot of what I'm talking about is sort of based on some things that Raf was saying about this class CX of Motivic exponential functions. And one important feature that Raf brought up was that you can talk about universal quantifiers, but not existential quantifiers, right? And so some results work only when you have universal quantification. And so we will have to remember at some point that if I want to say something about my reductive group, but it only comes as a member of a family with some parameters, then I'll have to be forced to say something about all forms of this group at once. Otherwise, I lose my universal quantifiers over just the underlying parameters that are defining these groups. So it'll become a source of a bit of a headache later, but if we get there. Okay? But for now, and if we just cared about classical groups, for example, then there is a much simpler shortcut by just defining them as subsets of GLN defined by clearly written equations. Okay. So, all right. So next, so we get ourselves the family of reductive groups, and so now, I said the goal was to try and talk about the representation theory of these groups, but so representations for us would be representations in complex vector spaces. So something about the homomorphisms from our G, let's say of QP arbitrarily, into the endomorphisms C of some complex vector space. These are necessarily infinite dimensional, well, unless they want to be one-dimensional, because of the topologies being so incompatible and so on. So this is what we would kind of like to do, but this is very far from what we can do. So as I've been kind of reflecting on this project for this talk, I realized that actually the only thing that we can do is get various results that are related somehow to orbital integrals. So what we can do is that we can handle orbital integrals, which I will define in a moment. And then, luckily, thanks to the work of Harishchandra and Wells-Bourget and a number of other people in the representation theory, a lot of the results you want to know about representation theory are somehow boiled down to results about orbital integrals. And so anything that we can reduce to orbital integrals, we can sort of handle, and nothing else, really. So, so the rest of this talk is going to be about orbital integrals. And so I better define such things. So yeah, so I will talk in parallel about things both on the group and on the Lie algebra. So given G, we also have its Lie algebra, which is geometrically its tangent space at the identity. Kind of, I mean, that's what would happen for the real Lie groups. For the p-adic groups, well, it's still a Lie algebra. There is well, it's a vector space with a Lie bracket on which G acts. So in my example, so my running example, G is SL2 or SL3 or something like this. The Lie algebra is a little SL2 is the set of 2 by 2 matrices with entries in the same field where G started with trace equals 0. So again, for classical groups, has very nice description, easier to classify than the group itself. Basically, over the algebraic closure, just classified by the root system. So in the same way as for the groups, we construct, basically at the same strike, once we have the fixed choice, we construct the groups with the Lie algebras as families of definable sets. And so we will have, stop, okay, so the definition goes in parallel both for the group and for the Lie algebra. So, well, G acts on itself by conjugation. Oh yeah, I'm a little bit sloppy, so what I should say here is maybe the G points, the group of G points over a given field acts on itself by conjugation, and on the Lie algebra by a joint action, which in all the classical cases, when we're thinking about G as a subgroup of GLN and the Lie algebra as the corresponding subset of all matrices, then this joint action is again just conjugation by an element of the group. So we'll just keep it at that. And okay, and now, so the two boards move and the third one doesn't, right? So at this point, so if, yeah, okay. So if I write something on this board, then we will never see it again, right? So, okay, so I think the board 2 goes up. The board 1 comes down. I'm sorry about this. I thought it would work better, but no. Stop. Oh yeah, no, that's fine. Yeah, that's okay. Okay, I think I'll just. Right. So sorry about this. Okay, so. Okay, so finally I can define the orbital integral. So it's orbital because it's an integral on the orbit of this adjoint action. So we take a function which is locally constant. So this CC infinity stands for locally constant, compactly supported functions. So this is exactly the class of functions that already appeared in Halupczok for the test functions. And so suppose we have x belongs to g of k. So I'm writing the Lie algebra version because this will be more useful to us, but a very similar thing can be done for the group. So this is our orbital integral. And this is basically an integral of this test function on the orbit, on the adjoint orbit of this element x. So I will write it as f of g inverse x g dg. Well, on what? So the orbit, just by the orbit centralizer theorem, is the quotient of g by the centralizer. So this is g of our field mod the centralizer in g of x. So centralizer in g of x is the set of g in g of k, such that g inverse x g is x. Okay, and so now, well, what is this dg? So I'll put this d dot g. So this is a g invariant measure on the orbit. And this turns out to be big source of various headaches. So how do you put a measure on the orbit? There are many ways to do this. And it turns out that some ways are easier to deal with than others for our purposes, but also some are more useful than others. So it turns out that somehow for the last several years, all I've been doing was thinking about orbital integrals, but sometimes with respect to different measures. It turns out that switching between different measures on these orbits is quite non-trivial. So excuse me. So one of the easy ways to define the measure is just take a quotient measure. So this seems like a really harmless definition, quotient of a Haar measure on G by a Haar measure on the centralizer. This centralizer, by the way, if x is diagonalizable over the algebraic closure, for example, which is the majority of elements, then the centralizer in itself is a reductive group, so it will have a Haar measure. And so, okay, both Haar measures are unique up to constants. So this quotient, you just have to choose some normalization of Haar measures, and you will have a quotient. So, of course, this quotient measure is unique up to a constant. And by the way, in any other way, if you somehow get an invariant measure on the orbit, it will just differ by a constant from your favorite one that you obtained this way. So these constants seem completely minor, but in some applications that maybe I will get to, they become quite important. Sorry?
One, the unit element has a basis of compact neighborhood which are groups.
Yes, so, yeah, that's right. So. Right, so if something like, so in our G, one easy example would be again GLN or SLN. So the basis of compact neighborhoods is just given by concurrence subgroups, right? You just put concurrence conditions on matrix entries and you get them closer and closer to the identity. Same in the Lie algebra, you have a basis of neighborhoods of 0, right? So you have a, yeah, these groups, G of K, they are, as topological spaces, they are locally compact, totally disconnected, kind of exactly the same way as our p-adic fields are, right? And you have a locally constant, compactly supported function. So, and then you're integrating it on the orbit, though. So the question is, so the intersection, so the orbit, right, it's a thin set of some codimension in UG. So it carries this quotient measure. So the intersection, this does not have to be a finite sum, right? Even though F is a linear combination of characteristic functions of balls, the intersection of a ball with an orbit can break into many, many little balls on the orbit. In fact, I was going to just, to give you a feeling for what these things are like, I wrote down an example which I copied from Kotwitz's expository paper, is on GL2. So, so this time it's going to be an orbital integral on the group, just because, I mean, they're all slightly different. The computation is slightly difficult. I did not recompute for the Lie algebra. So on the group, it's the same thing, but you integrate, instead of an element of the Lie algebra, you put in an element of the group here, but it's the same measure, same idea. So, by the way, I should have mentioned this. So there are two ways to think about, maybe before I do the example, I just want to advertise two ways to think about this orbital integral. So you can fix an f so you can fix the test function, then x goes to phi x of f is just a function on the Lie algebra. Or you can let the test function vary and fix x, and then f goes to phi x of f is a distribution, exactly in rough sense, a linear functional in the space of test functions. Or, well, I said two ways, but I guess as a mathematician I have to have 3 points here. So, you can also kind of combine these two ways, and you can take a family of test functions fa indexed by any, well, later definable set, and then you can look at the combined kind of situation when you send xa to phi x of fa, and then it becomes a function of both x and the parameter. This would be our preferred way of thinking about it, which kind of combines the first two ways. Okay, so now example on GL2. You can fix, let f naught be the characteristic function of just GL2 of the ring of integers. Right, then well, if your element gamma is diagonalizable, so gamma in GL2, let's say QP now for safety, is diagonalizable over QP, then phi gamma of this F naught is going to be Q to the D gamma, where D gamma is the valuation of 1 minus A over B. So diagonalizable gamma is diagonal matrix conjugate to a diagonal matrix AB over QP. So what we see is that as gamma gets close to the identity, right, if its eigenvalues get close together, then this thing will grow big. And D gamma is the valuation, it's not the absolute value. And then if gamma is something off diagonal, for example, lives, its eigenvalues live in a quadratic extension generated by square root of this epsilon, right? So this is something like a real Jordan block in our p-adic situation. So in this situation, the O gamma of F naught is going to be 1 plus Q plus 1 Q to the D gamma minus 1 over Q minus 1. Okay, now this board goes up. Stops, and this board comes. Okay. So I would like to make some comments about this formula. So there are similar formulas so this one was when the eigenvalues lived in an ramified quadratic extension. Oh yeah, I should write what D gamma is for that situation. It's very similar to the previous case. So in this case, D gamma is the order of 1 minus gamma gamma bar.
Sorry, what does Q mean P in the...
Oh, sorry, the Q is the P. I should have said, so sorry about it. I said QP, but I really meant a local field with residue field of Q. Apologies for that. Okay, so so the comments on the behavior of these guys. So it tends to get large as gamma goes to 1, and so this is so I've fixed a test function, right? So this moment I'm looking at something that's a function of an element gamma in G. It is locally constant, as you see, right? So it only depends on something like this, but the disks on which it's constant get smaller and smaller as you approach the identity. And something that's harder to see, so it contains some arithmetic information about gamma, meaning it kind of cares for where its eigenvalues live. And the third comment is that, it looks like it has some geometric series in it, all these things about q to the d minus 1 over q minus 1, and this really is reasonable. It does come from a geometric series. And this q plus 1, which looks very mild here, because we're just dealing with GL2. So this q plus 1 is the thing that contains the arithmetic information about gamma, so to speak. And it's known by the work of Hales and more recently Cheng-Chiang Tsai very generally. So it will have things like a number of points over fq of some hyperelliptic curve that depends on gamma for bigger groups. For example, when G is something like a big symplectic group and so on. So there are many examples known where the arithmetic information that so calmly encoded in this little q plus 1 there when I'm dealing with GL2, when your group gets big, instead of coefficients like q plus 1, so it will always have something like q to the power of the discriminant of gamma. That I will explain in a moment, I hope. But the coefficients of that wind up having really complicated arithmetic information in them. And they're not computable, of course, because you can't really have explicit formulas for anything like this. And so this is why these objects have been quite difficult to deal with. And thanks to the work of Harishchandra, a lot of the information about the representation theory of p-adic groups gets encoded in the orbital integrals. And then there is Langland's, who reduces some really serious questions to the fundamental lemma, where the fundamental lemma is an equality of orbital integrals living on different groups. I will say something about it. I will not state the fundamental lemma, but I will state what our project can do for it. Okay. And so, right, and so so what does Motivic integration have to do with all of this? Well, after all, it is an integral of a Schwarzbruch function, over something that clearly looks like a definable set. And so the first theorem, which in this form I think is due to Cluckers, Hales, and Lozère, approximately in 2007, which says that if you take f to be the characteristic function of the rank of integers of our Lie algebra, then x goes to this orbital integral is a Motivic function. Now, what is a Motivic function? So it's exactly as in Raph's talk. So this is an algebra of functions generated by, so this is class C. Raph was talking about class C exp. I will mention something about the exp shortly. But Motivic functions are an algebra of functions generated by definable functions.
Functions with values where?
Oh yeah, sorry, definable functions from, well, let's say valued field to the n. I will make this slightly more general. So normally you really care for valued field to the n, but you could, it's fairly harmless to allow parameters from the residue field or from z. But anyway, maybe I'll just leave it this way. So they're c-valued functions, but they're built from so this c is a little bit artificial. It's basically you're tensoring with c at the end. Your functions really are almost like rational valued. But let's see where they come from. So they come from definable functions from vf to the n to vf cross, to vf and n to z. You're allowed to do this, and also absolute values of definable functions. So this is the p-adic absolute value, right? So this is where you pick up, so these values are so here where f is from vf to the n to vf again. So this would take values in kind of the set of kind of p to the n, q to the n, where q is the cardinality of the residue field and n is an integer times z, right? So so these are really rational. So you might allow some denominators, but they're kind of rational valued functions. And so, and then, so you're making an algebra of functions generated by this, but you also want it to be closed under integration. And it turns out that the class of Motivic functions exists that satisfies this.
Sorry, what do you mean by functions from VF to VF?
Sorry, did I do something wrong? Could you just tell me what the right thing is? Yeah? Sorry? Oh, I mean from I think they're valued functions still. I'm sorry, I don't know. Where? Amy, what should I do?
Yes, here. So line above. VF to VF.
The complex number. What is the what do you mean by at the top?
I don't know. I'm sorry. I'm not understanding the question. So I
Yes.
no, VF is not a subset of C. So no. Sorry, I'm trying to say. Apologies about this. So no. Sorry, I see. This is just wrong. It shouldn't be there. So it was meant for the next line. So sorry about that. Yeah. Okay. So yeah, you can have something like yeah. Sorry about this. You have characteristic functions of definable sets. So it's so an example, or any z-valued definable functions. And so characteristic functions of definable sets will live here, and absolute values of definable functions from the valued field to itself will live here. And so then you're trying to make an algebra of functions that's closed under integration. By closed under integration, I mean that if you have a function on x times y, some f of x, y, where x and y are some definable set, and you integrate out the y variables, then it's still a Motivic function of x under good conditions. So the difference with Raph's class of functions was that Raph's class also had the exponentials. So what he had on top of all of this was the additive characters and additive characters applied to definable functions. And so yeah, we indeed can, many of our results will also apply to the CX class, and then it becomes also closed under Fourier transform. So maybe I'll just make a comment about it without writing it down, because it's somehow not essential at the moment, is so everything I say about orbital integrals, they will live in this class C of Motivic functions. But if you want to do a Fourier transform of an orbital integral, which is a perfectly valid distribution, then they will wind up being the CX class functions, and everything still applies. Good. Other questions? Yeah.
If you want to do it uniform in the value field as you do, you should have one extra generator, which comes from finite sums over the residue field. But that's just to close it up under integration. You need
Yes.
a little bit more.
Yeah, you need a little bit more. So that's what I'm saying. We're making it closed under integration. So I just decided not to go into that, but maybe I should have. But okay. So, all right, and so, right, so one theorem that we've stated already is that the orbital integral is a function of this class. And so now a comment about that is that maybe a more precise way to state this theorem is that there exists a measure on, there's a way to endow orbits with measures in such a way that it would become a function of this class, right? In the sense that so it seems like an almost trivial result, because the orbits do form a family of definable sets. You're integrating a definable function. Anyway, yeah, the function, this particular function is clearly definable. So you're integrating definable functions and definable sets, but the key is in the measures that live on those sets. So there are various ways of endowing the orbits with measures, and as it turns out, somehow the measures that I defined at the very beginning, that measure that's still on the top board, saying that's the quotient measure by some well-chosen measure on G and a measure on the centralizer, is kind of pretty hard to prove that that measure actually does fall under the scope of the measures that we can consider in the Motivic integration world. And so that maybe I'll make some comments about this. So let's see if this will, oh, no, stop. This one should come down, and this one should go up. And so, all right, so this gets us to orbital integrals in some sense being Motivic. And so the immediate consequence of this so the transfer results for the fundamental lemma. So the fundamental lemma basically is an equality. It says that, so if you have a group G and a somehow related group H, which is endoscopic to G, I will not define that for sure. So it says that there is a certain linear combination of orbital integrals, some finite linear combination, which is with very precise properties, equals some other finite linear combination of so I'll write F naught G, F naught H. Okay. Of orbital integrals on H. So the y's are related to the x's in a very precise form, like they have the same characteristic polynomials and so on. So anyway, so it's just an equality of well-defined linear combinations of orbital integrals. The F naught G is the characteristic function of G of O. This is the characteristic function of H of O. So okay, and so this was proved by Chao and Go in finite characteristic. And so immediately by knowing that this is an identity of Motivic functions, you get it for QP. Now the fundamental lemma story is not over, so this is just kind of one version. And there's a much more general statement that appears in the work of Langlands, and that's really needed. And so this is called the fundamental lemma for the unit element. By unit element, we mean that this guy, this function, this characteristic function of the maximal compact is the unit element of the Hecke algebra. So there is a more general statement. Same for, let's say, so you basically might want to change the test functions Fm. So in the case of SL2, to characteristic functions of, so this time I want to move on to the group, so I will take the integer points, the uniformizer to the m, the uniformizer to the minus m, 0, 0 times g of O. So you look at the double coset of the maximal compact subgroup generated by this diagonal matrix, so that's a pretty big set. And so for every m, you have this the characteristic function Fm. And now the problem is that in this identity of orbital integrals, this Fmh is something much more complicated. It does not go from just the characteristic function of such a double coset to the similar characteristic function of a double coset. It goes to some linear combination with well-prescribed coefficients coming from Satake transform. So, but there is a precise formula for what it should be. So each Fm goes to some linear combination of such things, okay? And so there is a result of Hales in the 80s, which says that in characteristic 0, fundamental lemma for F naught actually implies fundamental lemma for the full Hecke algebra. I will write it like this for Fm. You know, for a general group, you still do have a family of functions parameterized by tuples of integers. So it's not such a big lie to say this. Okay. And, but this is very much in characteristic 0 because it uses global methods which are not available in positive characteristic. So the interesting path of the general fundamental lemma now is just, it kind of goes in a slightly roundabout logic. So we have characteristic P and characteristic 0. So here in Go proves the fundamental lemma for F naught. Because of it, well, you know, you could either use Wells-Porget's method or you can use Motivic integration as just described. You get the fundamental lemma in characteristic 0 for F naught. So then you can use this old theorem of Hales and get the fundamental lemma for Fm. And then you can take it back and get the fundamental lemma for Fm in positive characteristic. And this is the work of Hales and, completely non-alphabetical. So it's Castleman and Seeley and Hales, and that's very recent. I think it's about 2016. Because so you take it back by transfer, because now what we have is a family of identities between these Motivic orbital integrals that are parameterized by the integers. So you have to do all this work by proving that these complicated coefficients are actually constructible, in some sense, functions of those integers.
Do you get this transfer for P big enough or for all P?
Oh, yeah, sorry, let's you get it for P big enough. So then there is kind of, there may be a path directly to prove the fundamental lemma by Ngo's methods and characteristic P. Bouthier was working on it, and I'm not exactly sure of the status. I think with some extra assumptions it's somewhat complete, but it's not completely general yet.
P much bigger than 0 is which step?
Sorry? P much bigger than 0 applies to the transfer. So for now, this result is only known in positive characteristic for P much bigger than 0. So yeah, of course, every time you have a transfer, it's for P much bigger than 0.
The other transfer is for all P, the first transfer.
No, this is also for P bigger than 0. So there's one issue here. So in the same theorem, it also, kind of in the same stroke with the trace formula, he proves that almost all P in characteristic 0 implies that it's actually true for all P. So this is an old, yeah, sorry, I forgot this step. So you get the transfer only for almost all P, but then because of that theorem, it's actually true for all P, and then you can transfer the whole thing back. So the same thing happened to the so-called smooth transfer conjecture of Langland. So there is a more refined one. So this is for characteristic functions of big sets, but there is a theorem which is kind of like the fundamental lemma for every element of the space of test functions. So it says that for every f in CC infinity of G, there exists fH in CC infinity of H, such that the identity of orbital integrals holds. So again, something like this, so similar to this theorem, there exists a theorem by Wells-Porget, which says that in characteristic 0, the fundamental lemma implies this existence of the smooth transfer. In positive characteristic, that wasn't known, and so Hales and I have proved it again by doing this and by transferring it from characteristic 0 back to positive characteristic. And the difficulties there is that this FH, you have no handle on it at all. It's not explicit in any way. Its existence comes because of some linear dependence and independence relations between certain Shalaika germs. And so you can't prove that this FH is definable if F is definable. There's just no way to do that as far as I can tell. And so it goes by complicated transfers of various linear dependence and linear independence relations, which goes back, and that transfer of dependence relations is possible thanks to the work of Raff and Imi on these loci of linear. You could make a locus of linear dependence and kind of locus of linear independence, but only the locus of linear dependence transfers. And this is where it kind of goes back down to the beginning of the talk, and that's where you have to remember that all your groups depended on some parameters and only the universal quantifiers transfer. And so then the whole thing becomes a rather complicated logical game of making sure that all these linear dependence relations that you never use an existential quantifier in the whole game, basically. So yeah, I think I said about half of what I was hoping to tell you about this project, but I think the time is up, and thanks.